Thank you very much for my presentation in our conference. Good day, ladies and gentlemen. I am presenting a paper, Skin Laws in Fragmentation Dynamic of Ceramics and Natural Materials. The work is carried out at the Institute of Continuum Media Mechanics Ural branch of the Russia Academy for Science in the Laboratory of Physical Foundational Strength. This is slide outline of the report. One, papers and motivation of the research. To review so the result of our laboratory work on the fragmentation of ceramics and natural materials, quartzite, quartz, sandstone, under various loading conditions and method of recording the processes of deformation and fracture. Review of the methodology for size or mass, fragmentation analysis, and fractal luminescence registration. For result of fragmentation analysis and fractal luminescence signals and analysis of the initial porosity of sample and the fracture surface of fragments. And conclusion. In introduction, the problem of fragmentation is fundamental of foliage groups of physical phenomena at scale, from ductile and brittle failure of materials. The fragmentation process exhibits the signal of critical phenomena and responsible scale laws. It implies the analysis of materials behavior depending on the loading energy near some critical point, which corresponding to the transition from materials with damage to fragmented materials. The critical behavior is fragmentation is investigation by analysis statistical fragments distribution depending on the material properties, ductile, brittle, its initial structures, porosity, loaded intensity. The fragmentation law describes the spatial temporal dynamic of defect evolution of this class of singularity and the final stage failure, which is typical of lower equilibrium critical system. The statistical fragmentation laws are associated with basic aspect of failure related to the nature of the singularity typical of critical phenomena, which are component in the case of failure by defect nucleation and near multi-scale interaction leading to the crack, nucleation and growth. As applied to fragmentation, this is manifested in qualitative change of fragment size, mass, statistical distribution depending on the material structure and loading intensity. The imperative defined statistical fragmentation laws as described by an exponential, logarithmically normal and power law distribution. The goal of our work is to experimentally study the fragmentation of ceramics and nature materials under various loading conditions and method of recording the processes of deformation and fracture basis on the study of the distribution laws of fragment size under condition of quasi-static and dynamic compression with joint registration of fractal luminance, shock wave loading. That will be contribution to the establishment of the relationship between self-similar laws of deformation and fracture with multiscale mechanism of fractal relaxation caused by the behavior microscope defects. The whole parameter of sample, ceramics, quartzites, and quartz has piezoelectronic properties, and sandstone are presented with this slide. By methods loading are presented on this slide in table below. For testing a sample which has piezoelectric properties was selected. Impulse loading was realized by the method of electric explosion of wire, including electrical scheme of electric explosion wire and photo of the experimental complex are presented on the slide, and includes a system of capacitor, a source of high voltage which provides electrical explosion of wire, and the formation of the shock wave propagating in the radial direction. The amplitude of the loading pulse was set by changing the energy on the capacitor battery. Quasi-static compression realized of the electromechanism universal testing machine performing any axial loading. Fractal luminescence was registered by two methods. In the first, the joint operation of the photon multiplier and oscilloscope was used. In the second, high-speed video camera was used, which recorded the destruction of the sample and fractal luminance. Dynamic loading of cylindrical sample by a Compkinson Kolsky bars setup. Fractal luminance was registered by photomultipliers and oscilloscope. The destruction processes of rock quartzite cylinders was accompanied by fractal luminance. The gloss was recorded in two ways, with a photomultiplier and high-speed camera, with which was able to record the destruction process itself. The resulting specimen fragments were identical in shape and size, regardless of the loading conditions. Sample fragments were sieved across sieve system and waves. The total number of fragments was counted on each sieve. This slide shows cumulative fragments distribution for quartzite sample obtained under quasi-static and dynamic loading. The curves have two slopes. Each load is described by a power law, which is typical for the distribution of brittle material. For large fragments, the power in the law was same for all samples. For small fragments, the degrees were different. Part of the curve runs below. This is possibly related to the formation of the fragments as a result of the large fragments break. We analyzed the time interval between fractal luminance pulse obtained by photon multiplied and an amplitude of present is my slide on the signal responsible to noise. Fig 10 shows the cumulative distribution of the number of time interval greater than a central specified from time interval between dumping of pulsed or the entire signal. For all sample of quartz, next sample investigation, the cumulative fragments mass distribution have a slime inflection and were well described by our function with a height approximation confident of R in degree 2, 0.96. We analyzed the time interval between photoelements pulse obtained by photomultiplier. The figure 12 shows the cumulative distribution of the number of time intervals greater than same specified from the time intervals between the pulses of the entire signal for sample 3 and the second part of the pulse for sample 5. This is shows the cumulative fragments mass distribution for sandstone samples obtained under dynamic loading. The curves have to slown with a small inflection obtained and different loading energize. The cumulative distribution are described by a
sorry, Irina. You need to go to the conclusions because we have a lack of time.
Okay.
Sorry for interrupt you.
Okay. And in conclusion, the result of the work are shown on the slide. Thank you for your attention. I'm sorry.